Next, your lecture number 5. We are going to learn about understanding probability and how to estimate probabilities to be able to use the standard normal distribution tables to understand sampling techniques, confidence interval, sampling error, and the other sources of error, and finally, the introduction to OLS regression. The probability function of a discrete random variable. What is a discrete random variable? Discrete random variable is a type of random variable that can take on a countable number of distinct values. For example, you roll a dice and what you get is either 1, 2, 3, 4, 5 or 6. You throw a coin or toss a coin, either you get a head or a tail. So discrete means you have distinct number of values. Random means when you throw a dice, it could be 2 or 6 or maybe 5 or 3. So suppose we toss a fair coin and there are two possible outcomes. Either you get a head and a tail, of course. That is the two number of possibilities we have. So what is the probability of head or tail occurring? Clearly, they are both equally likely to happen or occur. So it is of course 0.5 for each. Probability of getting a head is 0.5 and probability of getting a tail is again 0.5 or 50%. So fine, they are equal, but the important point here to learn is that the sum of their probabilities is 1. Like for example, India and Pakistan are playing and there is a 70% chance India wins. And there is a 30% chance Pakistan wins. So the combined probability has to be a unity, 100%. So note that the sum of probabilities is always 1 or 100%. So probability of getting a head, 50%, and probability of getting a tail, 50% means always 100. Probability distribution, this is what we're going to discuss. A random variable may be described by its probability distribution with the following characteristics. It quantifies outcomes with specific probability. That's what the probability distribution is all about. It quantifies outcomes with specific probabilities. Mean the average result, showing you the central tendency. What is the first moment of distribution, second, third? Let me explain the idea. Moment, basically it's a quantitative measure that captures various aspects of the shape of the distribution. The first moment is mean. We know what is mean, it's average. Second moment is variance. Third moment is skewness. And the fourth moment is kurtosis. I doubt that you will study the later two. So these are, you may say that these are some measures of or some aspects of the shape of distribution. So few of them we'll discuss. And then we want to be able to answer questions such as what is the probability of an event X occurring. That means we will use this probability distribution to calculate the possibility of a specific event. For example, the possible changes in a stock price. Events may be data observation like share price or any event that we won't like to predict. The normal distribution. Normal distribution is probably the most important probability distribution you would ever come across. There are many possible probability distributions, numerous, each describing different types of data and scenario. A few distributions capture the properties of a large number of variables. Yes, among these, only a few are particularly significant because they capture the properties of a large number of variables effectively. And one of these is the normal distribution. Yes, this is one of the crucial among all. It's basically the cornerstone in the field of statistics due to its ability to describe many natural phenomena, height, weight, for example. It says many variables are normally distributed around with different means and variances. What is more interesting about the normal distribution is that many variables in nature and human activities tend to follow this distribution, although they often do so with their own unique means and variances. However, we can standardize them to mean 0 and variance 1. Yes. To simplify analysis and make different normal distributions comparable, we can standardize them. So what standardization does? Standardization transforms any normal distribution so that it has a mean of 0 and a standard deviation of 1. I will show how it's done. So this process is very important in many statistical methods and tests. We will see as we proceed. This is your normal distribution with the mean at the center, 0, 1 standard deviation to the right, 2 standard deviation to the right, contains about 47.5% of data. And negative 2 standard deviation from mean contains the remaining 47.5 data. That means a total of 95%. Whereas 1 standard deviation from the mean, right and left, that is about 68% of the data. So this shaded area under the curve, it represents 95% of the total area, highlighting the probability of finding a point within 2 standard deviation of the mean. And this is very important. This concept is vital for understanding confidence interval, hypothesis testing, and many other statistical applications. We'll discuss these as we proceed. So this is what you will be seeing a lot in the next few slides. So how do we transform a normal distribution to a standard normal distribution with the mean 0 and the standard deviation 1? This is it. A normal distribution where x follows a normal distribution with the mean mu and sigma square is standard deviation. This can be transformed into a standard normal distribution using the z-score. This is the formula that we use to transform any score from a normal distribution to a standard normal distribution, and this is z is equal to x minus mu x upon standard deviation, where x is the original data point from the original distribution, mu x is the mean of the original distribution, and the sigma x is the standard deviation of the original distribution. So then finally we have successfully transformed a normal distribution into a standard normal distribution with mean 0 and variance 1 or standard deviation 1, both are 1. Now the question that we should ask, why are we doing this? Purpose of transformation. Why? This transformation is used to standardize different data sets so that they can be compared directly, or to simplify the calculations of probabilities and the critical values that you will use in your hypothesis testing. So by using the z-scores, data from different normal distributions can be converted to a common scale, and thereby we can then make comparison. We can make some statistical analysis, and then this will make things much more easier for us. So this means that z is symmetrically and normally distributed around mean 0 with a standard deviation of 1. What does it mean? It means that the standard normal distribution is symmetrical around its mean, which is 0, and it has standard deviation of 1. So this symmetrical property means that for any given value of z, the probability of a standard normal variable falls somewhere between minus z to positive z. So it's like right, that's what we do. We'll see it as we proceed. And then it further says that this transformation preserves the probability of an event occurring. What does it mean? When we transform a variable into the standard normal form through z-score, we will see how it's done. I'll just show you in a little while. It preserves the underlying probabilities. It means the probabilities stay the same. It's just that we have converted a normal distribution into a standard normal distribution. So this means that the relative likelihood remains unchanged. Even this transformation has been done from normal to standard normal. The likelihoods remain unchanged. Probabilities remain unchanged. Even though the scale of the data has been altered to fit to the standard distribution, normal distribution, but things stay the same. It's just that we have scaled them into a new form, but things remain the same. Probabilities remain the same. Next it says, once we calculate the probabilities of events occurring for the standard normal distribution, we can use these for all variables that are normally distributed. It means once probabilities are calculated for the standard normal distribution, these can be applied to any normally distributed variable. So this is because the transformation of data to standard normal form, it helps us to utilize the same set of probability calculation for any normal distribution by just simply transforming the values from normal to z-score. I will show you with an example. This will make more sense once we do some question. So here's a good example that should explain you the idea. Suppose we had data on returns to investments of £10,000 for many companies, and that the average return was 750. That's mean, with a standard deviation of £150. So what we have been given? We have been given the mean
750 pounds, and the standard deviation 150 pounds. Now we need to transform this into normal distribution. The returns are normally distributed with what is the probability that the randomly selected companies has a return of greater than 900 pounds, less than 500 pounds. We are going to transform this normal distribution into a standard normal distribution. Right, so the first step we do is to use the formula we just saw in the previous slide. Z is equal to X minus mu upon standard deviation. So for this, let's say call it Z1, 900 pounds minus 750, that's the mean given above, upon standard deviation 150. So when you simplify, it's 1. So this 900 pounds in the normal distribution represents standard normal distribution score of 1. So Z1 is 1. And the second part says less than 500. So for this, you apply the same formula, your Z2, that's 500 minus 750 divided by the standard deviation. And if you simplify, this gives you negative 150. It gives you negative 1.67. So now, what we have done, we have converted these numbers from the normal distribution to a standard normal distribution of score 1 and negative 1.67. How it is solved, let me show you. So for the first part where our returns of greater than 900, for returns greater than 900 pounds, it follows Z is equal to 1. So that means if you just look at the graph, this graph will highlight the area under the curve to the right where Z is equal to 1. So means we are somewhere in this region. And if you just look at the table for Z1, so 1.00 basically. So 1.0, so it means you're talking about this. So this region here represents 84.13% probability. Since we are talking about the region above this, since the total area under the normal distribution is 100, so 100 less 84.13 gives you 15.87. So it means the probability of getting a return higher than 900 pounds is 15.87 because we are in this region. Now let's do the second part. The second part, the returns are less than 500 pounds and corresponding score in Z was 1.67, right? So we are talking about somewhere here. So you'll probably fall in this region. So 1.67, 1.67. Now this completes the story. 1.67, and that's 0.9525. If this whole is 100, and of this part, this much is 95.25, then this region here is 100 less 95.25. So that means the probability you get is 4.75%. Right? So we got it. So there is a probability of 4.75 for returns less than 500 pounds. And for returns greater than 900 pounds, we calculated the probability to be 15.87 in the previous part of this question. So this is how we use the normal distribution. We convert the normal distribution to standard normal distribution, and then using the standard normal distribution, we can calculate the probability of any event falling within this distribution. Next, we have regression analysis, rather data and regression analysis. We discussed this in our previous classes. Regression analysis is a statistical method used in science and social science, including business and management, that involves all of the following 4 elements of the research process. Which 4? These. Theory, you set up a hypothesis, you get data, and then you derive your conclusion. We have already discussed this in our lecture 1. Now let's take another situation. Suppose a company wants to know how to be more innovative. It could carry out regression analysis to find out the variables that most strongly linked with innovation. So what do you think, what can these variables be? Yes, research and development, spending, employee skills and education, your organizational structure, intellectual property, technological adoption, your market orientation, your company culture, your collaboration and partnership with universities and research institutions, your financial performance, your environmental scanning. There are many factors. So we would like to see which of these factors is strongly linked with innovation. Starts from the theory and formulates a hypothesis. For example, X causes Y. Spending on our research and development causes innovation. Let's say. So OLS is a way of testing this hypothesis of fitting data to models. OLS regression starts with a theoretical framework where you hypothesize a relationship between X and Y. Just like the example, innovation and your spending on research and development. Next, we set up a hypothesis. OLS provides a statistical method to test these hypotheses by fitting the data to the model. It aims to explain the dependent variable Y as a function of independent variable X. So OLS utilizes analysis of variance, covariance, and correlation. This we already discussed. OLS employs these tools and they will help us measure the spread of Y values, covariance, which measures how much two variables change together, correlation, which measures the strength or direction of the relationship between two variables. We discussed this in detail in our previous class. The simplest regression method is ordinary least square, also known as the classical linear regression model. Yes. So this model, let's say we have these data points. So this method calculates the best fitting line for the observed data by minimizing the sum of squares of the vertical deviations, these, from each data point to the line. We will discuss this in our coming slides shortly. Next, we have types of data variables. So category and quantity, they represent the two main types of data variables used in our statistical analysis. First, we have category. Ordinal. Ordinal means variables where the categories have a meaningful order. That's why the word ordinal, from order, or ranking. And the intervals between these are not necessarily equal. For example, you may rank dissatisfied, neutral, satisfied, very much satisfied. So this is what you call ordinal, such arrangement, like satisfaction rating. Then we have nominal. Nominal means variables that can include categories without any ranking. For example, male, female, young, old, type of car, hair color. So nominal means they are just category without any intrinsic ranking, no ranking in them, just categories, categorizations. Then we have binary. Binary is a special case of nominal variable where there is only two set of possibilities or two categories, such as yes or no, true or false. And this binary word has been driven from information technology, zeros and ones, I'm sure you know. Then in the next category, quantity, we have two types of variable, discrete and continuous. Discrete means something that can be counted, like number of students in a class or number of cars in a parking lot, right? Or when you throw a dice, what you get is a discrete number, 1 or 3 or 7, not 7, 6 of course, or 5. And continuous means a numeric variable that can take any value within a finite interval, like weight of students in a university, could be any number between 50 kg to 150 to 200 kg, right? And similarly, height. Height can also be any variable within a finite interval. So these variables can be measured and then subdivided infinitely. So why do we have to study? Because understanding these types of variable is extremely important, because the choice of statistical analysis or the techniques that you would use largely depends upon the nature of these variables, right? For instance, correlation and regression analysis requires either continuous or ordinal variables, right? Here we have some examples, some variables, but what type? Make of a car, Fiat, Volkswagen, BMW. This categorization is nominal, because these are categories without any inherent order or ranking. Then we have condition of car, excellent, good, or poor. Clearly, it's ordinal, because these categories have a clear ordered arrangement on the quality or condition. But the intervals between these categories are not necessarily the same. Price of car, What do you think? Yes, continuous. The reason, price can vary continuously over a range and can be as little as $10,000 to as high as $5 million for custom built car. Yes. Length of a car, 2 meters, 2.5 meters. Again, it's continuous because even though we have been given these two, but length is a measurement that can theoretically take any value within a range, so making it a continuous variable. Transmission, manual or automatic. Clearly, it's nominal because these are the categories that do not have to have any order or ranking. Age of car, again, age of car, if expressed in years, it's discrete. Age of the car is typically counted in whole numbers, 1 year, 2 year, 5 years. So it's a continuous variable. And number of seats, again, it's discrete because the number of seats is a countable number because seats have to be whole units. And again, the question, why are we studying this? Because understanding these classification is crucial for selecting the appropriate statistical method for analysis. So once we know we have a discrete variable, our analysis will be in the different direction. Introduction to regression analysis. Our underlying principle that is guiding our research hypothesis, that is a testable prediction about the relationship between variables, and those variables can be quantitative, continuous, binary, and scaled. And finally, the OLS estimation of parameters. Variable and parameters in regression analysis. The classical linear regression equation, two variables involving y and x, where y is the dependent variable. Dependent variable, also called the outcome variable. It is the variable we aim to predict or explain, right? And in our model, y depends upon x. Then we have x, the independent variable, also referred to as explanatory or predictor variable, because this is the variable we believe has influence on y, or this is the variable that describes y. It's an independent variable and this is the dependent variable. Then these two coefficients we see here, beta 1 and beta 2, are parameters that estimate y OLS. We will estimate y OLS. Beta 1 is the constant term or intercept, and beta 2 is the slope coefficient, the gradient of the regression line. And the subscripts, I takes the value 1, 1, 1 throughout, or 2, 2 this way. So we have 500 companies, and it would run from 1 to 500, representing each of these 500 companies we are discussing. We take the dependent variable on the y-axis, vertical axis, and explanatory variable on the x-axis. Alright, here we have years of schooling plotted on the x-axis and the hourly earning on the y-axis. And as you can see, the year of schooling is from 0 to 20, and your earnings showing on the y-axis from minus 20 to 120. So what do we see here? Each dot you see here, each dot here represents an observation in the data set. In this case, it's the individual's hourly earnings. Like, for example, a person who has had 7 years of schooling earns this much, or a person that has 11 years of schooling earns this much per hour. So yes, there is a lot of variability. Despite this variability, there appears to be a general trend where hourly earnings increase with the years of schooling. Alright, so statistical inference may be defined as the ability to make inferences about a population from a sample drawn from that population. Let's say this is the case we are discussing, the years of schooling and the hourly earnings. So we can't ask everyone in the US how many years did they spend at a university, or what is the total years of education and what they earn. So of course we can't. So suppose we define the population as all citizens in employment in the US. So we can't ask every single person in the US. So further, suppose we collect data on 500 employees in the USA and ask them about their incomes, their education and other variables. We can't ask everyone out in the entire US population. So we have taken a few. So these few are called samples in statistics. Under what condition will this sample of 500 provide a good guide to the relationship between income and education in the whole population? Because based upon our result on these 500 individuals, we are going to make some some conclusion or some inference about the whole population. So what we can accurately infer from this sample? What confidence can we attach to estimate of B1 and B2 using the sample of just 500 employees? Right? So we are going to make generalization based upon these 500 employees. So to make generalizations from the sample of 500, we need to know that our estimated parameters, intercept and slope for the sample, these 500, they reflect the true parameter in the population of all employees in the US. So these individuals we have selected our sample, they are representative sample, and their intercept and slope, that is B1 and B2, are a reflection of the true parameters of B1 and B2 for the whole population in the US, whole population of all employees in the US. So this is crucial. Now the question is, how many individuals would we need to look at? Or what sample size, 500, 1000, 10,000 or 100,000? So what sample size would we need to gain an accurate estimate of the average income of employees? So, and how should we select employees? There are different sampling techniques. Let us discuss. So first sampling method is the random sampling, means pick every 10th employee that you come across. Second, we have stratified sampling, means stratify sample by some category, like industry, steel industry, computer industry. So stratify sample by some category that affects income. Cluster sampling, it focuses on particular geographic regions or areas. We call clusters, normally in order to cut cost of data collection, because it involves a lot of cost when you're collecting data for your statistical analysis. Stratified sampling, all members of the population must belong to one stratum and industry. Means every individual in the population, such as all employees in, for example, must be assigned to one specific subgroup, and that subgroup is called a stratum. Then, no employee can belong to more than one stratum. Individuals can only belong to one stratum, ensuring no overlap between subgroups. Within each stratum, employees should be similar. Yes, this is called homogeneity within strata. Members within each stratum should be similar to each other, which enhances the effectiveness of the sampling by reducing the variance within the stratum. Stratification is known before sample is collected. That is, we must define industries and know which industry each employee is in. Means criteria for stratification must be established before the sample is collected. This would ensure that the sampling plan can be appropriately designed to represent the population accurately. It says stratified sampling reduces sampling error as compared to simple random sample, but raises cost. Yes, this is true. Your stratified sampling, since it's more detailed, hence it is more accurate, random sampling can carry mistakes and errors. Cluster sampling. Identify geographic areas or clusters, means you select natural groups or clusters within the population based on geographical areas. These could be regions, cities or neighborhoods. Each cluster should ideally contain a representative cross-section of the population. It means each chosen area should be a small version of the larger population, meaning it should include people with different characteristics, means, or items with different characteristics. That, in fact, that smaller version you have selected represents the larger population. That is the basic idea. Then select a limited number of areas from the total number, ideally using random sampling. Yes, you can only pick a few areas from all possible ones because of limited time and resources. So this is usually done randomly to make sure that it's fair. Then it says for each area or cluster, select a subsample from the population in that area. Within each chosen area, pick a smaller group of people to study. And then finally, combine the subsamples from each cluster to obtain a sample. Put together the data from each sample group to form one big sample, and you use this to help you gather data more easily when studying large populations spread out over wide areas, like we're talking about the population, the working population in the US. Next, we have quota sampling. Often used for market research and opinion polls. Yes, quota sampling is often chosen for market research and surveys to understand the public opinion. Sample size is determined, for example, 1,000, usually by cost clearly. The number of people surveyed is usually set based on how much it costs to reach out to as many respondents as possible. Each interviewer, researcher is given a quota, a number of respondents to attain. For example, 1,000. Yes, each researcher or interviewer is assigned a specific number of people to survey. For example, they might each need to talk to 1,000 people. The quota may be stratified by age, firm, gender, employment type. Fine, yes, this is true. This is a combination of quota plus stratification. So the overall quota is broken down into smaller groups based on characteristics like age, the company they work for, or the gender. So this helps ensure that the sample reflects different segments of the population. Quota sampling, continuing. Quota sampling is low cost and quick to produce results. Yes, quota sampling can be very economical and fast, making it appealing for quick studies or when the budgets are low. However, it is often unreliable. Yes, although it's cost effective, no doubt, quota sampling can sometimes lead to unreliable results. So this is because the method doesn't always select respondents randomly. Then off-cited case of the market researcher who quickly achieved their quota by interviewing people queuing for a train at, for example, at King's Cross Station. The survey was on gambling and the queue was for a special train to Newmarket races. So this clearly is an example where market researcher quickly filled their quota by interviewing people in a specific location, here, King's Cross Station, who were in a queue for a train going to Newmarket races. So this scenario can introduce a bias. Why bias? Because the survey was about gambling and those who were interviewed, they were not the representative of the general population. So this is the issue with quota sampling. Difficult to know the representativeness of the sample. This is also an issue because it is hard to know how well a quota sample represents the entire population. So this uncertainty can make it difficult to generalize the result to a broader group. Next, we have sampling error. When the population is large, let's say 1 million, different samples of say 1,000 may differ from this population and each other in terms of mean, median and variance. Yes, you have, this is the whole population and you have selected samples of 1,000. So they will differ from the population and they will also differ from each other with regard to their mean, median and variance. Each one of them will have its separate mean, median and variance. So this, not only they differ from each other, also they differ from population. So when this is the case, then these samples are not representative of the whole population. So this variability leads to sampling error. As sample size increases, sampling error falls, but not in linear way. Means as you keep on increasing the size of sample, let's say you increase it to 10,000, then the sampling error will decrease, but not in an exact linear fashion. I will show you what it means. Consider a large population, all employees in the UK in millions. How big does our sample have to be? 500, 5,000, 50,000, 500,000. So how big does our sample have to be in order for it to be representative of the whole population? And what are the error margins on particular sample size for a large population? Let me show you the next slide. It shows that if you survey 500 employees from a large population out of 1 million, then we can be 95% certain that the margin of error will be 4% plus or minus. But when we increase the sample size from 500 to 1000, look at this, the margin of error decreases, and if you increase it to further 2000, your sampling error decreases to just 2%. So this shows that as you expand the sample size, the sampling error decreases, but not linearly. Not linearly means this. Sample size, as the sample size increases, as you can see, 50 to 100 to 200 to 1000. So as the sampling size is increasing, the error margin decreases, but it decreases diminishingly. It decreases at a faster rate of decrease. That's what it is. Non-sampling error. First, sample selection bias. This happens when the way we pick who to survey, maybe our selection is wrong. For example, only serving people who have internet access might miss the opinion of those who do not have internet access. Response bias, it occurs when people don't answer questions truthfully or accurately. They might want to look good or might not remember things correctly. Failure to contact some individuals who should be in the sample. Yes, sometimes we can't reach out everyone. We need to reach for our survey. So they might not answer calls, or we might have the wrong contact information for them. So this could mean we made a mistake. Errors in transcribing or recording data. Yes, errors can also happen when you're putting survey answers into a computer. When you're tabulating the results, you can make mistakes. So this could be because of maybe typing mistakes or misunderstanding what someone said. Next, drawing together lecture 1 through 4 and applying them. That's we've discussed earlier. We can construct abstract models of a more complex reality. We can derive hypotheses from these models. We can test these using statistical analysis. And we need to be aware that when dealing with samples of data, there may be sampling errors that we've just done. Let's discuss and let's think of a research question. What determines a person's income? It depends upon a lot of factors. It depends upon occupation, experience, the industry he's working in, location, gender and age, economic condition, size of the company and the profitability of the company, and then the education and skills. There could be many reasons. So the point here is that what determines a person's income could depend on many factors. Let us be specific. Let us define a specific hypothesis, that relationship between education and what a person can earn. That's our specific point of inquiry. For example, hypothesis that time spent in education has an impact on hourly earnings. That's the main focus of our study. So we assume that the relationship is linear. That as you spend more time studying, your earnings would be higher. So here's a model of individual's earning, where E1 denotes earning of individual 1, EI, and this is driven by the years of education. And then this beta 1 and beta 2, they represent the intercept and the slope respectively, right? For individual 1, for example, it's going to be E1, B1, B2 and S1. For individual 2, it's going to be E2, B1, B2 and S2, because each one has different years of education and then it drives his earnings. So this is our model for individual earning. Now let us explore how we can test this hypothesis. Objective understanding regression analysis. Ordinary least square method. It's a statistical technique we use to estimate the parameters of linear regression model. We want to find estimates of beta 1 and beta 2 for our regression model. So these parameters will help us understand how changes in the predictor variable X will associate with the dependent variable Y, right? So parameters that we're going to estimate are beta 1 and beta 2. They are called coefficient in the regression model. Beta 1 is the intercept and beta 2 is the gradient. And this has been repeatedly discussed. This has been repeated. So we will take data on two variables X and Y. Once the data is collected, we will then put it on OLS and then see how we can determine beta 1 and beta 2. This is our independent variable years spent in education X, also called the explanatory variable or predictor variable or independent variable. And this is why the hourly is earning. That's what we want to determine or call the dependent variable. So this relationship takes the form Y is equal to beta 1 plus beta 2, this is the gradient of the line, times X. Note that we have hypothesized that beta 2, the slope of the line, this is the slope of the line. Slope of the line is positive, clearly it is positive, and it is significantly different from 0. This means that more time spent at university or in education raises earnings. That what we have been discussing for the last 4 lectures continuously. So we further assume that the true relationship between two variables is linear, positive, We estimate the relationship using sample of data on x and y by fitting the regression line through scatter plots so as to minimize the errors or gaps. We'll discuss shortly. And two parameters, x and y, define the line with beta 1 being the intercept and beta 2 being the slope. You have already done it in principle. What it says, note that we did this in week 2, in our lecture 2, by hand eye when you drew a straight line through the scatter plot, so there's no need to be worried because we have already done this previously. Now we're going to be more precise using the method of OLS to derive estimates of beta 1 and beta 2, that we call them B1 and B2, and we are going to derive the formula for beta 1 and beta 2 that are on your formula sheet. I'll explain what those formulas are. This is your scatter diagram again, and the same scatter diagram with the regression line. This is the regression line. Now suppose that the variable y is a linear function of another variable x with unknown parameters beta 1 and beta 2 that we wish to estimate. As you can see, it's a positively sloping line. Now suppose that we have a sample of 4 observations with x values shown here. Look at this. So if the relationship were an exact one, so what you see here, you see the observations would lie on a straight line here. This, 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 and this. Right? We would have no trouble obtaining accurate estimates of beta 1 and beta 2 because the points are clearly on the line. Like these, Q1, Q2, Q3, and Q4. But the problem, in practice, most economic relationships are not exact, and the actual values of y are different from those corresponding to the straight line. So what we have, these are the actual observations or actual values. So there are certain divergences. See here, this, 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 this. So to allow for such divergences, we will write the model again with a new element in it as where u is the disturbance term. So this u here represents this gap between the observed value and the value what it should be under the perfect relationship. So each value of y thus has a non-random component. This is the value of y. Let me point specifically here. It has two components. One is the non-random component, this part, predicted by the model, non-random component beta 1 plus beta 2 x, and a random component, this part, a random component u. So this first observation has been decomposed into these two components, the non-random component and the random component. So absence any regression line, in practice we see these 4 points, P1, P2, P3, P4, showing a positive correlation but not an exact one. So obviously we can use the P points to draw a line which is an approximation to the line beta 1 plus beta 2x. If we write this line as y hat, that is the in statistics, the y hat means that's the predicted value of dependent variable. So y hat is equal to b1 plus b2 x, where b1 is an estimate of beta 1 and b2 is an estimate of beta 2. So this line here, this line is called the fitted model, and the values of y hat predicted by it are called the fitted values of y. Right? They are called fitted values of y, and they are given by the heights of point, this r1, r2, r3, and r4. So in this particular line, again there is a discrepancy. This is the value predicted by the model, but this is the actual value. So the gap between R1 and P1, these are called the residuals. So this is the residual for point 1, point 2, point 3, and point 4. So this is the actual value. This is the fitted value, and the gap between actual and fitted value is called the residual. These. And they are not the same as these, because this line is our original line we were discussing. This is the original model we are talking about. So these variances from the line are called disturbances. And this difference between actual and the fitted line values, they are called residuals. So remember, residuals are not same as disturbances.
So here we have the diagram that shows the two unknown relationship as well as the fitted line. This is the fitted line and this is the true unknown relationship. Now let us differentiate between the disturbances and residual just on a single figure, single diagram. These are residuals between the fitted value and the actual value. This, then this, then this, then this. So these are residuals. And the disturbance term, this is it. This is the one, the unknown relationship from this point up to this actual value. Then this. Then this. And this one. They happen to be the same. Continuing, the disturbance term in each observation, this is the disturbance term. This, 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 and this. So it says the disturbance term in each observation is responsible for the divergence between the random component. This is the random component. This part, let me take another pointer. This random component, this, 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 this. And the true relationship in the actual observation. This is it. So it's more or less repetition, but just I want to make sure that you understand it well. Whereas the residuals are the discrepancies between actual and fitted. Actual, fitted, actual and fitted. This actual, fitted, actual and fitted. So it says if the fit is good one, the residuals and the values of the disturbances term will be similar, which means these two lines will lie over one another. But they must be kept apart conceptually. But the idea is if the disturbance and residuals are the same, then these two lines tends to be the same. So using the theoretical relationship, Y can be decomposed. This is Y. It can be decomposed into its non-stochastic component, that is the fixed component, this part, and the random component, this. The other kind of decomposition we can make is with reference to fitted line. So you can see fitted line plus residual gives you the actual value. So actual value has two components. Actual value Y is equal to fitted line, this part, plus residual B1, B2x4 plus residual E4. But look at this. Here the actual value, this. So this actual value is equal to fitted line less residual E3 minus E3. So here this is the actual value. It is equal to fitted value less residual E2 minus. And here the actual value has two components, fitted value plus E1. So E1 can be an addition, or E's can be, the residuals can be added or deducted to reach the required point. So in each observation, the actual value Y is equal to the fitted value plus or minus the residual. Plus or minus the residual. And then it says this is the operational decomposition which we will use for practical purposes. Next we have least squares criterion. Minimize the residual sum of squares. What does it mean? It means E4 squared, E3 squared, E2 squared and E1 squared. That will in fact change the sign. All the negatives will become positives when we take squares. And why is it so? Let me explain. So why don't we just take the residual? The reason is here. The answer is that you would get an apparently perfectly fit by drawing a horizontal line through the mean value of Y. Look at this. Let's say if this is minus 2, this is minus 3 plus 5. So these residuals tend to cancel each other out. And so can we assume that this line is the perfect fit? So instead we take squares. See how. You must prevent negative residuals from cancelling positive ones, and one way to do this is to use the squares of the residuals. So that's what we've done here. Minus 3 squared plus 9, minus 2 squared plus 4, and this 25. So our objective is to minimize the sum of the squares of the residual. The sum of the squares of these residuals has to be minimum. Only then we will have a line that will have the shortest distance between itself and these residuals. So we want to draw a line that has the shortest distance amongst these residuals. So the line that is perfectly fit within the residuals. So this is what we want. We want to minimize the residual sum of squares. And you now know why don't we just minimize these residuals itself. We want to minimize the sum of squares.
Alright, now let us derive the coefficients B1, B2 using OLS. To derive our estimates of beta 1 and beta 2, which we call B1, B2, we use the method of ordinary least squares. Let me take you to the next slide where we have actually calculated using formulas. Look at this. This is your fitted line. We want to derive the equation of this fitted line. For this we have two coefficients we need to determine, B1 and B2. Let us find B2 first. This is the formula we will use to calculate B2, and it is nicely solved on the next slide. This is x minus x bar times y minus y bar summation divided by summation of x minus x bar squared, least square. Alright, so here we go. Here we go. Calculation is quite simple. These are the number of students. Books read represent your x. Marks obtained represent y. Okay, let us first calculate mean. Add all these and divide by 5, we get x bar. Add all these, divide by 5, we get y bar. So this is basically y bar, 54. 2 is x bar. So x minus x bar, that is, x bar is already there, you have 2. So it's going to be x minus x bar, 3 minus 2, 1. 1 minus 2, minus 1. 0 minus 2, minus 2. 4, 2 minus 2, 0. And then finally 4 minus 2, 2. So then we get y bar, y minus y bar, 56 minus 54.8. 56 minus 54.8. 57, then we deduct all these. These are y minus y bar. So x minus x bar into y minus y bar will give you this column. This will be this part of the formula, numerator, and then so this 39 will serve as the numerator, and then x minus x bar squared, this is the denominator. So 39 by 10, that gives you 3.9. So we got 3.9 as your B2. So now, and how do we find B1? B1 can be calculated using this formula. B1 is equal to y bar minus B2 x bar. Just plug in the numbers. So B1 is equal to 54.8, and B1 we just calculated to be 3.9. Let's plug in the numbers. So it's going to be 54.8 minus 3.9 x bar, which is 2. So if you simplify, B1 would be, after the simplification, it gives you 47. Now we got the equation. Now we got the equation of the fitted line. It's equal to B1 47 plus B2 we calculated with 3.9x. This is the equation of the fitted line. So here are some results using SPSS. We got 47 as your constant, which you call the y-intercept. Basically this is the intercept representing the predicted exam mark when the number of books read is 0. Even no book is read, this is what a student will get. So it indicates that if a student doesn't read any book, their expected exam mark would be 47. Okay, this is what we determined just now. This 3.9, this is the slope of the regression line, indicating that every book you read, your exam mark will increase by 3.9%. 3.707 standard error of the constant. This measures the variability or the precision of the intercept 47. A smaller standard error indicates more precise estimate, and a larger standard error indicates a less precise estimate. Next we have this 1.513. This is the standard error of B2. As I told you, smaller standard error here also indicates more precise estimate. This is beta coefficient, which we calculated in our previous classes, I guess in lecture 4. This is the beta coefficient, which measures the strength of the impact of books read on exam marks. Means you read more books, you get more marks. So it's standardized across all variables. A beta close to 1 or -1 indicates a strong effect, and a beta that is 0 has a weak effect or no correlation. So here 0.83 suggests a moderately strong positive impact of reading books, means you get higher score. Then here we go, this is T statistic for constant. This is the value that is clearly far away from 0. So a high absolute value far from 0 typically indicates that the intercept is significantly different from 0. And here we got 2.577 for B2. It is greater than 2, so a value greater than 2 or less than -2 usually suggests statistical significance at 5% level. Finally, we have the last column. This is the p-value for constant. This p-value tests the significance of the intercept. A value that is less than 0.05 usually indicates that the intercept is statistically significant. So for books read, we have 0.082. This p-value tests the significance of the slope, B2. Since 0.082 is greater than 0.05, so it suggests that effect of books read on exam marks, while positive, is not statistically significant at 5% level. So this is the result you get by running the data through SPSS. So what is the summary of all this, what you see on your screen? So the summary is that this model that we have discussed, it suggests a positive relationship between the number of books read and the exam marks, with each additional book read associated with an increase of about 3.9% increase in your exam score. However, this relationship is not statistically significant at the conventional 0.05 level, which means that we should be cautious in concluding a direct impact of books read on exam performance based upon just sample data we have. So the point here is that the intercept is significant, yes, 47, suggesting that the model effectively captures a base level exam performance, but we cannot conclude that the more books a student reads, the higher would be his score. So here we have a scatter graph that shows you the hourly earnings against year of schooling. This is what we've been discussing, and this is for a sample of 150 respondents. Okay, so what else? It shows you that grade 13, 14 and 15, this one clearly represent the first, second and third years of college, clearly, and of course the 16-year education means grade 16 means completion of your 4-year college. Higher grades indicate years of post-graduation, of course, after your graduation. Alright, so this is the output from a regression of earnings on years of schooling using Stata. So what we get the constant coefficient negative 13.93, that is debatable, and then we have the slope or the gradient to be 2.45. Let us interpret what does it mean. So for the time being, we are not interested in standard error and t-scores. For the time being, we will be concerned only with the estimate of the parameters, the constant and the slope. So here the S is the coefficient 2.46, which we termed as B1, and the intercept estimates is negative 13.93, that is B2. So what does negative mean? This is interesting. This negative 13.93, what does it mean? It says that a person who has no education, with no years of education, would have to pay 13.93 per hour to be allowed to work. That doesn't make any sense at all. Why would you pay to someone to get work? So this doesn't make any sense at all. But an interpretation of negative payment, it's impossible to sustain. I mean, you don't pay to get work unless you are paying bribe. So let us try to make some interpretation out of it. To do this, we will enlarge the marked section of scatter graph, this part only. So this is the enlarged part. It says that after completing 12th grade instead of 11th, earning would increase by 2.46. So 1 year of education gets you $2.46 additional, and 15.53 in journal tendency. Now you should ask yourself whether this is plausible figure. It is implausible. This could be a sign that your model is misspecified in some way. So it says that for low levels of education might be plausible, but for high level it would seem to be an underestimation. Just few dollars per hour when you move 1 year of education in a university. So that doesn't make much sense. So we have issues both with the intercept as well as with the gradient. So a safe solution to the problem is to limit the interpretation to the range of sample data, just some specific range, and we refuse to extrapolate. Extrapolate means, let's say we may try to determine that a person who's got 18 years of education, what should we expect his earnings to be? This is extrapolation. We can't do that. We shouldn't be doing that. So we refuse to extrapolate on this basis that we have no evidence outside the data range. So just some limit part of this graph would make sense, but beyond the range it doesn't give any plausible numbers. Another solution is to explore the possibility that the true relationship is non-linear. It's curved. As you gain more years at a university education, the earning increases exponentially. So, and that means that we are just approximating it with the linear regression. So we will soon be extending the regression technique to fit non-linear models soon in our later lecture. So for now, what we have done, we have estimated the relationship between two variables x and y by fitting straight line through sample points x, y. That's what we've done. We learn how to calculate the distance between the line and the observed points. Further, we have just the sample data, so we do not know the true relationship. And finally, we can test how good our estimates of beta 1, beta 2, which is B1, B2, are using a t-test. So that's what we've done so far.